Okay, folks, so I wanted to record this video mostly to get you to see some of the concepts on classification that we started talking last two classes, especially last class, and how in fact perceptrons are able to classify linear perceptrons versus how they actually fail in some cases, and then how the neural networks, the multi-layer neural networks, would wind up being useful. So to do this, actually it turns out that this playground.tensorflow.org is a nice little tool that you can play with. If you just search for Tensorflow Sandbox, you'll find this. So I'm basically just going to make you follow along as I play with it, and then you can play a lot more on your own browser window. Okay, so if you see what's going on here, there is on the top you have the learning rate. You can set the learning rate to anything you want. Activation function, remember the different kinds of activation functions. We will just pick sigmoid function for now, and we'll not care about regularizations right now. In the problem type, I'm going to pick classification. And then in on the left hand side in the bottom here, you can change the ratio of training to test if you want. I'm just going to stay at 70%, and then I can actually make the data less versus more noisy. So if you notice, currently I selected the current data, which here on the right hand side there are some blue dots and some yellow dots. The interesting thing is that there is actually they're almost linearly separable. There's like a line you can draw that separates them. If it, because of the noise, to the other side of the line too there are some blue dots, so there's no actual direct single line. If you reduce the noise to zero, then the blue and red are like very and yellow, blue and yellow are completely separated. That's the difference between noisy versus non-noisy. The thinking, you can think of noise essentially as the possibility that the data is classified wrongly even in the training data. So there were some blue dots, they are somehow being classified as yellow, and some yellow dots, some that are being classified as blue. And of course, in those cases, the learning systems essentially have to find a way of classifying that sort of reduces the aggregate error. That's what we looked at. So minimizing the error. Okay, so then I am going to, and then you can play here by adding hidden layers. You can add, hidden layers, any number of hidden layers. So for example, now there are 2 hidden layers. I can add neurons, extra neurons, etc. And then basically at that point you can start training and so on. So before we start talking about the hidden layers, let's just remove all the hidden layers. And this is just a simple perceptron. So essentially a single linear unit. Okay, so now I have only the inputs x1 and x2, and notice that the output, essentially there are these 2 numbers calling test loss and training loss. Those numbers tell you how well is the learner doing in reducing the loss on the training data, that means error on the training data, and how well is it doing in reducing the error on the test data. Okay, so in this particular case, now I'm just going to start. So by just playing, pushing this play button, and you'll notice that when I press the play button, very quickly, the test loss and training loss have converged. So test loss has become, so the training loss, for example, has become 0.08. The test loss is 0.127. It's 0.127 because even in the best case, it drew the best possible line between the blue and yellow or orange, except on the other side the expectation is that on one side of the line should there be blue and the other should be orange. But since the data itself is noisy, you do have some blues on in this particular case on the left side of the line. Okay, so, and as the number of, on the top you see the epochs, that is the training epochs continuing, and then so it's sort of as the training epochs continue, you see how the training loss, the test and training loss changes. So we stop this here. Then I basically reset. Okay, now if for example set the noise back to 0, something like this, and then I restart again, this time you would expect that the last two basically grow down to 0 in both cases, because there's a very clean way of separating the blues and yellows. So not surprisingly, in this particular case, the linear perceptron is able to get training loss 0 and test loss 0, as you can see. Okay, so that's pretty good. We'll stop that there. And then what I want to do now is I want to pick a different data set. Okay, so let's see, I pick this data set. So here what is happening is that it's kind of, you can kind of see that there is no single line that you should be able to draw. Remember, this is all connected to the point I made at the end of last class, saying that in essence what perceptron is doing can be seen as taking the linear weighted sum of the inputs and checking if it is above or below a threshold, which is like saying it's sort of looking for a hyperplane separating the positive examples from the negative examples. In this particular case, you can see there is no single hyperplane that separates the blues from yellows. Okay, so in this case, if you try to train the perceptron, you expect that you will have a problem, because in the best case, it would still essentially have pretty high test loss. Okay, let's just see what happens. So I'm just starting this. So basically, you realize that the test loss is still 0.5. Training loss is 0.5. So that's basically, any line you draw, you will essentially have half of each of the kinds of the blue or the orange will be on one side and the half will be on the other side. There is no single line you are able to draw. Okay, and if you change the noise, essentially all it is doing is that it's even worse. Previously, the blues and yellows were in different quadrants. Now they're also seeping into each other's quadrants. So it will be pretty just similarly as bad. So there is no single line it is able to draw. The test loss is still quite high, and the training loss is also quite high. So as you can see. Okay, now at this point, consider the following thing. Suppose, remember I said, in fact, there was this example I was doing last class where I said, what if you started taking squares and products of the input features and you took linear weighted sum of that? Now, when you do that, essentially, it's still a linear perceptron. It's just you increase the number of input features. You are getting input features x1 and x2, and you're deriving additional input features by squaring them or summing them, etc. So in fact, if you see on the features column here, not only do you have x1, x2, you also have x1 squared, x2 squared, x1, x2, sine x1, sine x2. So notice that if I know the values of x1 and x2, I can compute the values of each of them, each of these other features. In doing so, in essence, you are increasing the dimensionality of the input data. The interesting thing is, actually, it could help in linear perceptron finding a way of classifying this data. So for example, if I were to pick also x1, x2, okay, so now I have x1, I have x2, and I have a feature x1, x2. Now, if I reset and start again a training, you notice what happened. Suddenly, essentially, there's a nice clean green region, the blue region on the top quadrant, and the bottom top right quadrant and the bottom left quadrant, and the yellow regions on the other two. Okay, and then suddenly the test loss and training loss reduce significantly. In fact, if I stop this and I change the noise to 0, change the noise to 0, so that basically the yellows and blues are in their own quadrants, of 4 different quadrants. Then if I retrain, you notice that essentially the loss is completely minimized. Okay, the loss is completely minimized because you have a nice little blue And perceptron, the single unit perceptron is able to separate the blues from yellows quite neatly. Okay, that's a very interesting thing. So what is happening is that even though the data is not linearly separable in the space x1 x2, it is actually linear separable in the three-dimensional space, including x1 x2 and x1 x2. Now what's happening essentially is, you can understand that when x1 x2, so if in this particular case, in this data, the quadrants, so x1 x2, if you take the sign of the x1 x2, it will be all positive here, okay, and all positive here, because this one x1 and x2 are both negative. Multiplying the product in the bottom left corner will be all positive, and top right corner will be all positive. Whenever the product is positive, I can say it's blue, and whenever the product is negative, I can say it's orange. And that's basically what Perceptron figured out for you. Okay, and notice how the training loss has become small. And then one other thing I want to show when I'm having this right here is what happens if I do different kinds of activation. So instead of sigmoid, let's say if I used tanh activation and then reset it and started it, then essentially the boundaries, kind of the shape of the boundaries might change a little bit. That's basically the kind of thing that winds up happening. So you should play with other kinds of activation functions. Okay, so